Hello everyone. Alternating current part 2. AC through inductor, capacitor and LCR circuit. These are the topics that will be discussed in this video. So first we shall see about AC voltage applied to an inductor. This shows a circuit with an AC source applied across an inductor. An inductor does possess some resistance, but we can neglect this. Now using Kirchhoff's loop rule, we can write sigma of E of t is equal to 0. That is V minus L into di by dt is equal to 0. Here L is the self-inductance of the coil and di by dt is the induced current due to self-inductance. Now we can rearrange this equation so that di by dt is equal to V by L. Now V, which is the alternating voltage, is given by Vm sin omega t, where Vm is the peak voltage. Now to get the value of current in this circuit, small letter I, we have to integrate Vm sin omega t by L dot dt, which is negative Vm cos omega t by L omega plus C, where C is a constant. It can be found that the value of constant is 0. Now using trigonometric identity, we can write cos omega t as sin omega t minus pi by 2 and Vm by L omega as Im. Here L omega is equal to XL or inductive reactance. This is a quantity which is analogous to resistance in the case of a resistor. Inductive reactance also has got a unit of ohm. Now after comparing alternating voltage and the current functions, we can see that there is a phase difference between the voltage and the current. We can see that the current lags behind the voltage by pi by 2 or 90 degree. Now we can draw a phasor representation of this circuit. This is the phasor representation of this circuit as shown in figure A. In this, the two vectors V and I are having an angle 90 degree between them. And B shows the two waveforms, that is one for the voltage and the other for the current, and these two waves are having a phase difference of pi by 2. Now we can find the average power in an inductor. Now the instantaneous power P is given by the product of voltage and current, that is equal to Vm sin omega 2 dot Im sin omega t minus pi by 2. Now sin omega t minus pi by 2 can be written as negative cos omega t. Hence this equation reduces to negative Vm Im by 2 into sin 2 omega t. As we know that sin 2 omega t is equal to 2 sin omega t cos omega t. Now the average power P dash can be found out by integrating over the interval 0 to t, where t is the time period, divided by t, which becomes 0. Now we can see about the magnetization and demagnetization of an inductor. This is a graph which we can use to explain the process of magnetization and demagnetization of the inductor with respect to the varying current and voltage. Now we can explain the stage from 0 to 1. In this case, the voltage V is reducing and the current is increasing. And since the current is increasing, it induces a magnetic field in the core of the inductor coil. Now, in this stage, since the voltage and current are having positive values, the resultant power is also having a positive value. Hence, energy is absorbed by the inductor from the source in this stage. Now, we can see the stage from 1 to 2. In this case, the voltage reverses its direction and the current goes on decreasing. And since the current goes on decreasing, the core of the inductor gets demagnetized. Since the sign of voltage is negative and that of current is positive, the resultant power is negative. Hence, energy is given to the source from the inductor. Now, from 2 to 3. In this stage, the direction of current is reversed and hence the magnetization is also reversed. And since the current is increasing in the reverse direction, the magnetization increases and the poles are switched. In this stage, since current and voltage are both negative, energy is absorbed by the inductor. Now from 3 to 4. In this stage, the voltage is positive and current is negative. Hence, the energy is given to the source from the inductor. And since the current goes on decreasing, the core gets demagnetized. Now we can see the case of an AC voltage applied to a capacitor. This is a circuit showing a capacitor C connected to a AC voltage source. Now the voltage across capacitor is given by Q by C, where Q is the varying charge and C is the capacitance of the capacitor. Now in this circuit, by using the Kirchhoff's loop rule, we can write Vm sin omega t is equal to Q by C. Now the alternating current I is given by dq by dt. That's equal to omega cvm cos omega t, which can be written as I is equal to Im sin omega t plus pi by 2. Here Im is equal to Vm by 1 by c omega and 1 by c omega is equal to Xc, which is the capacitive reactance, which is a term analogous to the resistance of a resistor. As we observe the equations for voltage and current, we can see that there is a phase difference of 90 degree between them. The current leads the voltage by 90 degree. Now we can see the phasor representation. The phasor representation shows that the current leads the voltage by 90 degree. Now in B, we can see the two waveforms, that is one for the alternating voltage and the other for the alternating current. And these waves are having a phase difference of pi by 2. The power in the case of a capacitor circuit is also 0. Now we can see the charging and discharging of a capacitor. So from 0 to 1, that is when the voltage increases and the current decreases, the capacitor gets charged. And since voltage and current are both positive, energy is absorbed by the capacitor. Now from 1 to 2, the current gets reversed and hence the capacitor gets discharged. And since current is negative and voltage is positive, power is lost by the capacitor to the source. Now from 2 to 3, the voltage increases in the reverse direction, and this results in charging of the capacitor. And in this case, the current and voltage are both negative, and hence energy is absorbed by the capacitor. Now from 3 to 4, as the direction of current is reversed, more charge accumulates on the capacitor and the charge of the capacitor increases. Now we can see the case of AC voltage applied to a series LCR circuit. An LCR circuit is a circuit consisting of an inductor, capacitor and resistor connected in series with an AC voltage source. Now, if we apply the Kirchhoff loop rule to this circuit, we get L di by dt plus IR plus Q by C is equal to V. Now we have to find the value of small I, which is the current flowing through the circuit. Since all these circuit elements are in series, the current flowing through all these elements is the same. There are two methods by which we can solve this equation. First method is by using phasors. So first we have to plot the phasors. We know that in the resistor, V and I are in phase. In the case of capacitance, the current leads the voltage by 90 degree, and in the case of an inductor, the voltage leads the current by 90 degree. Now in B, we plot the vector representation. Now I is equal to Im sin omega t plus phi is the current in this circuit, where phi is the phase. Now VRM, which is the voltage across resistor, is given by IMR. VCM, which is the peak voltage across capacitor, is given by IMXC, and VLM, which is the peak voltage across the inductor, is given by IMXL. Here XC and XL are the reactances. Now we can write VL plus VR plus VC is equal to V. That is the total voltage applied to the circuit. Now looking at the figure B, by using Pythagoras theorem, we can write Vm square is equal to Vrm square plus Vcm minus Vlm the whole square. That is, substituting the values, Vm square is equal to Im square into R square plus Xc minus XL the whole square. Therefore, Im is equal to Vm by root of R square into Xc minus XL the whole square. That's equal to Vm by Z. Here Z is known as the impedance of the LCR circuit and is given by root of R square plus Xc minus XL the whole square. If the LCR circuit is inductive, that is, if XL greater than Xc, then the current lags the voltage by phase. And if the LCR circuit is capacitive, that is, Xc greater than XL, then the current leads the voltage by phase phi. Now, from the figure B, we can obtain the impedance triangle. And from that, we can write tan phi is equal to Xc minus XL by R. Tan inverse of Xc minus XL by R. Now, this is the second method of arriving at the solution. That is the analytical method. In this, we write I is equal to dq by dt. Therefore, the equation L di by dt plus Ri plus q by c is equal to V becomes L d square q by dt square plus R dq by dt plus q by c is equal to Vm sin omega t. Let it be 1. Now, we know that q is equal to qm sin omega t plus theta, where theta is the phase difference. Therefore, dq by dt is equal to qm omega cos omega t plus theta. And d square q by dt square is equal to negative qm omega square sine omega t plus theta. On substituting these values in 1, we get qm omega into r cos omega t plus theta plus xc minus xl into sine omega t plus theta is equal to Vm sine omega t. Now if we multiply the numerator and denominator by z, it becomes qm omega z into r by z cos omega t plus theta plus xc minus xl by z sine omega t plus theta is equal to Vm sine omega t. Let it be equation 2. Now let r by z is equal to cos phi and xc minus xl by z be sin phi. So phi is equal to tan inverse of xc minus xl by r. On substituting these values, the equation 2 becomes, that is, by using trigonometric identities, we can simplify that to omega z cos omega t plus theta minus phi is equal to Vm sin omega t. Now we have to compare both these sides. So Vi is equivalent to Qm omega c, and we can write Qm omega is equal to Im, and theta minus phi is equal to minus pi by 2. So theta is equal to minus pi by 2 plus phi. Now we know that I is equal to dq by dt. Substituting these, we get I is equal to Im cos of omega t plus theta. Now for theta, it is minus pi by 2 plus phi. Therefore, I is equal to Im sin omega t plus phi. So this is the end of this video. In this video, I have discussed the circuit for inductor, capacitor and an LCR circuit to which an alternating voltage is applied. If you have got any doubt, please comment in the section below. Thank you.